Okay, so first of all, I would like to thank the organizers for just giving us to attend such a great event. So I'm really impressed by all the talks we have heard, and especially today, just coming from the very first one, which is a kind of what I did for my master and PhD, so it's really exciting, these high-pressure experiments. Then we came to the excitonic physics, so I'm also going to touch it a bit, so it was, again, really amazing. And finally, we ended up with something which I'm going to discuss today, so probably I should have go home instead of bothering you with exactly the same stuff. Well, nevertheless, still, I'm happy to be here, and I will just try to give you some flavor of what we are doing in my group in the Faculty of Mathematics and Physics of the Charles University, which is in Prague, the country's neighbor of Germany, Czechia, just by the way, for those who don't know. Okay, so as I had really great introduction of the whole week, and just the recent talk gave us the introduction even to this, what the Magneto-Raman and Magneto-PL is. So I will jump directly to the picture of our lab, which is here. So essentially, we are doing very much similar stuff as was just introduced in the previous talk. And besides like many low temperature and high magnetic field experiments down to millikelvins and 20 Tesla static magnetic fields, we are also much more focused nowadays in the optical techniques introduced in this extreme environment in some sense, also including some pressure experiments, but I'm not going to talk about this today. So just to give you some flavor, what we have, so our system is much more old school in the sense that we are operating 14 Tesla standard liquid magnet, the vertical one. It just has some kind of like advancement by means of the damping, so just to be able to get some reasonable signals out of there. And I will go to some like scheme. So this is like one possible setup which we can use in the experiments. So the part from Atopube is sketched here. So it's that what my colleague here said, it's the stick, the Atopube stick we are using. So essentially we have the piezo stage here, and also we are just much more like big fans of the free beams compared to the fibers. Specifically, we are much more interested in polarization. And in fact, the system is then coupled to various environments. So here I have the sketch for the Raman spectroscopy system we are using. So this is our design. We can go roughly to like 4 reciprocal centimeters with Stokes and Autis-Stokes regime. We can do the full polarization analysis as well. In the same time, we can also do these operando experiments because we have many collaboration in this optoelectronic direction. So they always require us to have the experiment, the combination of some optical excitation with light of specific hetericity compared to the measurement of transport, magnetotransport, or even some other characteristics they want us to do. So this is like the sketch. Beside this standard Raman measurements we are mostly doing, and I will talk about it later, we are also doing standard PL experiments, either in the static and also time-resolved regime. So for that, we have the system from picoquant equipped with several wavelengths. So this is also something which might be of your interest. So just to use my time properly, I will briefly jump to one of the first examples, which will be very simple. So I will just now stick only to photoluminescence. And in fact, I have noticed that during the whole week, we have discussed many interesting systems, just different types of 2D materials coupled together, stacked in a very clever way, or just having different twist angles and so on. Recently, we also had a very nice talk about how we can introduce the defects and get single photon emissions and so on. Nevertheless, I have really not noticed any system which we can call kind of mixed dimensional heterostructure. So I decided to give you some idea. And this week, we also heard this very nice word, PowerPoint physics. So now I will do kind of PowerPoint chemistry in that sense. So here we introduce a monolayer of TMD. So in this case, it was molybdenum disulfide. And then on top of that, we deposit molecules. And in this case, our goal was to get the coupling of the specific kind of molecules, which we call single molecule magnets, and they are well known in the community as being quite great representative for spin qubits, and to couple them to the TMDs, and by optical means to be able to read and write the quantum states of the molecule. Nevertheless, before we started to really go down to the millikelvin temperature, which is mostly our playground, we also explored the materials at standard temperatures, and we observed quite interesting features. And in fact, we all know, and just heard many times this week, that if we are kind of like looking to the Valley physics in TMDs, specifically at room temperature, definitely we don't get much like Valley contrast, simply because this like interval scattering processes and so on. So we really did not expect that we will be able to see something when we just apply the standard like chiral light exploration of the system in the way. Nevertheless, I'm already showing what we get even at the room temperature. And those are already the degrees of valley polarization. So simply the experiments is done as usual. So we are just maintaining like one helicity of the light. So let's say just right-handed, sending to the system. And either we like depolarize and get the efficiency, or we just simply send on the analyzer the complementary or same helicity, and we just record the signal. So this is how we get the original PL spectra. Of course, we are just doing some kind of mapping as well. So this is just spectrum collected from one point. And what we saw immediately, that at the position of the A exciton of the TMD, or in this case a molybdenum disulfide, we got quite like reasonable value of this valley polarization, which is something really unexpected. So we just try to repeat the experiments many times, even using different wavelengths. And then we change the wavelengths, the feature completely disappears. Even that when we were close to the resonance with the A exciton, we would expect that we will get indeed a higher valley polarization. So then the question was like, what is the reason behind that kind of unusual phenomenon? And for that, we look much more into detail in the interaction of these like single molecule magnets with the TMD. And of course, on the very general level at the beginning of the discussion, so everybody consider, okay, so we have species which is magnetic. So intrinsically, there is some magnetic moment in the center atom in here. So it's nothing else than terbium or dysprosium, lanthanide 3+ ion, and they're like just two ligands which are like sandwiching the magnetic atom. So there might be some spin-dependent charge transfer or something which is behind this effect. Well, when we explored more into the detail, the basic formalism, which is just used to describe the valley dynamics in TMDs, we found out that it's definitely impossible, and it just makes no sense to think in this direction. So instead, we just try to develop an alternative model. So like all the details for the formalism and everything is just given in the paper. So I will just try to very briefly describe it on this simplified sketch of the electronic structure. So here we have some like ground state, so some, in this case, like valence band, so we don't have the curvature here. We have this conduction band, and typically what we gain when we are exciting one type of the valley with one like specific helicity, we populate some like reservoir of excitons, of course, just they undergo some radiative recombination. That is clear indeed. Nevertheless, there are always like states which are non-radiative, and those are the states which are kind of spoiling the valley coherence in the sense that they are just simply contributing to the change of the like external dynamics in the radiative reservoir, and simply this is something which is behind the loss of the valley coherence. Nevertheless, in this case, we observe that just by some lucky energy management we have in the system, like these non-radiative states, which are just populated roughly in this area, if we just consider that we are at the like room temperature, so the phonons or the phonons will be kind of like thermalized in this tunnel 25 or 26 millieV, and we are like able to get something which we call this close to resonant Coulomb energy transfer, non-radiative energy transfer to the states of the molecules. So if we excite the whole system with a wavelength where the molecular states are not populated, so simply we are out of the resonance with the molecule, those non-radiative states can be trained to the states of the molecule. Then, of course, they recombine. Then we have some complementary emission of the photons of the terbium phthalocyanine molecule, which is definitely not overlapping with the excitons from the radiative zone. So consequently, due to this like energy drain from these non-radiative states, we are capable to boost the polarization of one valley. So once we switch the polarization of light and do the same experiment, so we get exactly the same result. Nevertheless, if we change the wavelength of the incident laser we are using for the excitations, everything disappears. And this is simply because of the fact that we are now able to populate the states of the molecule, because we are now in the resonance with the molecule. So in that sense, we cannot deplete this reservoir of these non-radiative excitonic states anymore. So consequently, we are just undergoing exactly the same exciton dynamics or like valley dynamics as we are supposed to have in the pristine molybdenum disulfide. So this is one example, very simple one, how one can use this chiral or circularly polarized light to look into valley physics, not only in this very nice and complex 2D materials-based systems, but also we can just extend it to some mixed dimensional structures and even into some more complicated materials. Nevertheless, I would like to go a bit further, and I would like to show you kind of very recent result, maybe a controversial, but I saw that this system is very much of interest in the community. So I decided to show it, and I will see what you can say to me after that. So I will start with some very simple overview of the Magneto-Raman scattering. So probably we have already heard in the previous talk. So we are mostly looking into Raman intensities. So this is the simplified term, which is proportional to the square of this term. So we have this incident and the outgoing, so the scattered light, which can be represented in the most simple approximation as some Jones vector formalism, which is very convenient when we are calculating the selection rules and so on. And then, of course, we have something which is important. This gives me the symmetry restriction by means of the material, which has some specific crystal structure. So it has some specific point group can be assigned to that. And based on this consideration, one can get quite easily the standard term, the standard form of the Raman tensor. Nevertheless, we don't have to forget a very important point, which is that, of course, this is something which works very nicely in the paramagnetic regime. So it means that for the formulation of the Raman tensor, I can simply use the point group symmetry, which is related to the material. At the same time, I'm fine, even if there are some local magnetic moments, still I'm in paramagnetic state. So technically, when I will look from the point of view of magnetism, I can assign only a specific gray group by means of the Shubnikov theory. So in this case, still in paramagnetic regime, we are fine. We can use the Raman tensors as we are used to and simply just describe all the phenomena we can observe in our spectra. Nevertheless, the situation changes when we are coming into the magnetically ordered state. And there could be two important features we have to consider when further analyzing the data. First, in some materials, and this is indeed the case of this chromium triodide, for example, we do have a structural phase transition. So it means that the original point group is no more the correct symmetry to be used to formulate the Raman tensor. But this is still simple. We just take different point group and just make some change to the metrics, and that's it. Nevertheless, because of the onset of magnetic order, we are definitely breaking the time reversal symmetry. And because of that, the Raman tensor in general cannot be formulated not only using the point group symmetry, but we also have to include one of the specific co-representations by means of the Shubnikov point group, right? So fortunately, the world of 2D magnets is kind of, I always say, black and white, because for most of the magnetic structures which are commensurate, we can use one of these black or white representations, so we don't have to make some more advanced corrections. Nevertheless, that's something which is very important, because we can sometimes observe features which are assigned to some phonon-like changes, but typically it's just something related to the fact that once we are driving the system to the magnetically ordered state, and due to this time reversal symmetry breaking, I must always think about this colored group co-representation to be involved properly in the Raman tensor. So then what happens? Well, we can have indeed a change even in the optical phonons. So it means when I have a representation for the optical phonon, which is, let's say, multiply degenerate, we most likely will observe some splitting due to this time reversal symmetry breaking. Then, of course, due to the normalization of the Raman tensors, we will have completely different selection rules. In some specific cases, it is not the case, but in general, it definitely works like this. Then we can even activate some normally inactive Raman modes. So this is another important feature. And finally, this splitting of these double degenerate modes, that's something which is even more complex, because sometimes we observe splitting even in the single degenerate representation. But it's something which is related to some extra effect related to interaction with other types of quasi-particles. So indeed, it's really important to properly assign all the bands by means of the symmetry and also the type of representation which is describing the corresponding Raman mode. Okay, so this is just some very general recap what we have to take into account when we are looking to our data. And in fact, I would like to mention one of the very first work which I liked. And this is the use of this Magneto-Raman scattering, not only to look into magnetic order and changes in the symmetries and just looking to magnon population and so on, but it can be indeed used as a kind of complementary tool to construct magnetization by means of temperature or magnetic field of this really tiny 2D magnets. Because imagine when I would like to measure magnetic moment of 2D magnetic materials, indeed I cannot use a squid or VSM because it will be super tiny, especially if we get some very small flakes from our colleagues to be measured. Still we can use some nanosquid approach, but then we are limited by the upper field where this nanosquid is still functioning. So in that sense, those optical techniques are very convenient, even tough diffraction limited, we can still get quite nice information about the magnetic order. So this was like one of the work from 2020, where people introduced the using of Magneto-Raman scattering, using the light with different polarizations on the vanadium triodide material. And you can see, like here are some representative spectra for different helicities of the light used for incident and outgoing beams. So you can nicely see that the red and black lines are alternating, so it means that we are definitely having some quite big differences between the intensities of the Raman peaks, like one of the important Raman peaks in this vanadium triodide with respect to the change of the incident and ongoing polarization. And it can be also theoretically derived that this change of the intensity is directly proportional to magnetization, or spin density in some sense. So once we just make this exercise in the whole hysteresis cycle, for example, we are able to reconstruct the hysteresis curves quite efficiently. So once we have a system where we have strong enough spin lattice coupling, like it is in vast majority of the 2D magnets, one can profit from using this Magneto-Raman scattering in the sense that we can really reconstruct the hysteresis curve. Again, the same thing can be done with the PL. So there are definitely many works that people just reconstructed magnetization from the chirality resolved photoluminescent measurement. Nevertheless, I value the fact that in the Raman scattering, you gain much more information because we are directly looking to those quasi-particles, not just this absorption and emission of the photonic field, but you can also, once there are some not very trivial changes in the Raman spectra, you can even go more into detail and look what is really behind. If there is some coupling to other type of quasi-particle, or if there is some structural change, or anything weird. So that's really something amazing. And one can really profit from the power of the Raman spectroscopy in that sense. So I have already mentioned that due to this spin lattice coupling, we can really construct magnetization processes. We can also look to different type of quasi-particle couplings. I will show it later. And finally, there is also another quite interesting field which popped up recently, and this is the exploration of chirophonons. And to me, it was always kind of controversial because people presented, just they have the chirophonons, so they did much the same type of experiment like here. But surprisingly, they had the chirophonons always in the magnetically ordered state, right? So it definitely means that what was measured was not really the chirality of the phonon, but simply due to the spin lattice coupling in the material, which does undergo the magnetic order. Simply they looked into this kind of processes. So that's very sensitive. Nevertheless, still there are some studies, and just also one part of our research is that we can really use the chiral light to detect these very interesting species, which are typically behind some upconventional processes in some TMD materials-based heterostructures. So I don't know how much time I have. I believe that I'm almost at the end, so 3 minutes exactly. So now I will show it. This is the system I have seen on many posters here, which is the chromium sulfur bromine, or bromium sulfide. And in fact, we got a nice crystal from our colleague. I will acknowledge him later. And well, the question was, can you do something with that? Okay. So in the very first measurements, we did this standard kindergarten exercise, temperature dependence of the Raman spectra for different helicities, and we were able to construct by fitting some critical exponents, just really to assign the features of the magnetic order and so on. And in collaboration with our colleagues who are doing additional calculation of the phonons, so we were also able to assign all the phonon modes, etc., etc. So far so good. Nevertheless, we were still interested what happens if we cool to the ground state, so to some reasonably low temperature, and apply magnetic field, and at the same time vary the helicity of the light approaching our sample. So in fact, the motivation was clear, and I think we have seen it several times here. So in this material, in the ground state, if you have like several layers, you will just mostly promote the antiferromagnetic order. And in quite reasonable field, which is something 1 and something Tesla, you populate the ferromagnetic state. So there is fields older magnetic phase transition to the ferromagnetically ordered state. And that's something which has been traced in transport. It has been traced in photoluminescence and so on. So definitely, we were interested in reproducing these data, and at the same time, we were interested in like reproducing the data by means of the Magneto-Raman scattering. So I'm showing like one example. This is like one characteristic Raman mode of the chromium sulfur bromine. Here I just picked up like one characteristic spectrum in 10 Tesla. But let's first look here. So the black one corresponds to the 0 field spectra. Then you like just start to change the field up to 10 Tesla in this case. We have here such kind of like pronounced maximum. And obviously, we have here some kind of split, which if you look to the representation, indeed, we do not expect a kind of split here. And then it just follows this way. So if we look to the map, which is shown here, and just to be on safe side, we are like shining with like right-handed polarization, and on the analyzer we are detecting like the same helicity of the light. Here is the like magnetic field axis. Here is some like false Raman intensity. And what you can see, if we go from the 0 to the positive like values, we observe here some maxima, and indeed there is this kind of like broadening, or if you look much closer, it's really some evidence of the splitting of the peak. If we go to the opposite polarity of the magnetic field, there is nothing, which is not that surprising in case we are like using this positive or this right-handed helicity. Definitely, we should be sensitive more preferably of one type of the like spin density population. So this is still fine. Nevertheless, just on the previous slide, you have seen that we can use this technique to reconstruct magnetization. But once I would plot the intensity of this feature, indeed, I will never get to magnetization as I would expect it should be. So it was really surprising. So we just did many experiments at the same time to be able to really confirm that we are still getting the same result, which was indeed true. And then we think, OK, so first, there is this type of splitting. Second, there is this unusual behavior. So there must be some extra quasi-particle coupling in the system. And yes, as it is. So when we did some complementary PL measurements, indeed, besides this, what is very well known, we also observed some enhancement in this high magnetic field. And when we applied some like further theoretical exploration to the problem, and also looked to different types of modes where it behaves complementary, and when we did some complementary excitation by means of the selection rules and symmetry consideration, we arrived to the point that indeed what we are seeing is really some spin parity-driven coupling of the excitonic states and the phonons in the material. So that's really something amazing. So that's why I just decided to share it with you today. As I don't have much time, I will just recap that I hope I have convinced you, on top of my colleague, which convinced me really, that the Magneto-Raman scattering is indeed a great technique to explore like-values phenomena in 2D materials. Nevertheless, what I believe is even more fancy nowadays, and the direction in our field, as we have seen here many non-trivial spin textures, going beyond the light, which is just chiral. So typically, the community is now just trying to implement the light, which is not only chiral, but it's structured, so it has non-zero orbital momentum. So I believe that then we will have really access to like much more wide range of quasi-particles and processes in the system in near future. So I would like to acknowledge, first my colleagues from the Hayrovsky Institute of Physical Chemistry. They are running the samples on collaborating. Most importantly, Webhub, my postdoc, and Haider, who is now group leader in Helmholtz Center Dresden, and also Zdeněk Sofer, the guy who provided us the crystals, so just recap of our yesterday's great poster session, and my theory colleagues Artur and Richard, who helped really a lot with formulation of the formalism we needed to describe the data properly. Thank you very much for your great attention. Just I have to thank also the funding as well, as I'm committed by the grant agreements, and I'm happy to answer questions. Thank you.